Hey everybody, it's Mrs. Levin. I'm here to introduce chapter 12 and 13, all about solutions in aqueous systems, and talk a little bit about their colligative properties as we go on in this playlist. All right, so first things first, what are the different types of mixtures that we can have? We can have solutions, we can have colloids, and we can have suspensions. All right, so solutions, that is more than just the answer. A solution is when you have something called a solute being dissolved in a solvent. Okay, the solute goes into the solvent, making a solution. All right, this is what we refer to as an aqueous systems. So this is going to be like your salt water, NaCl, hydrochloric acid is an aqueous system, or even when we had our copper sulfate, it's not liquid, it is aqueous. It is made with water. The two things dissolving in one another is referred to as going through the solvation process, as in to dissolve. Okay, that's where we get solvation from. It's not salvation with an A, like what you see at church and hallelujah and all that kind of stuff. All right, but a way to remember this is that you can fit into a vent. All right, but a vent cannot fit in you. And that would be pretty painful. All right, so you could fit into a vent. Ute goes into the vent, U and the V, but the V could not fit in you because that would be very bad if somebody vented through your chest like that. But you could fit into like a storm vent or an air vent or something like that. This process of solvation is going to result in either an exo or endothermic process, which thermic means heat. So it will either take in or give off heat. So if it takes in, it's going to feel cold. So that's going to be like an instant cold pack. Exothermic would mean that it would get hot, and you'll see more about that in this chapter and later on when we get into kinetics and energy in chapters 16 and 17 unit. Okay, so the other type of mixture is going to be a suspension, suspended in midair. All right, it pretty much means the same things. The particles are suspended in the solvent. They are so big that they would actually settle out unless you're constantly stirring it or agitating. So you need some type of moving water, most likely, when we're talking about our suspensions. All right, so muddy river water is going to be muddy until it calms down after the day after it rains, and then you'll see that it'll become clear again. And you all have seen, I'm sure, the pink stuff. Hopefully you're not allergic to it, but if you are, you found out the hard way. This is an oral suspension. Before you take any of the pink stuff for an ear infection or anything like that, you need to mix it. You need to shake it. You need to move the water. Because if you don't move it, all of the antibiotic is going to be at the bottom and not in that first dose. So you're going to get an uneven dosing. And we want to make sure that we do have an even dosing so we can get you feeling better right away. All right, and then the third type of solution is going to be a colloid. Okay, and a colloid is this weird gray area that picks up all the other kinds of substances that you might not realize are mixtures. All right, colloids are not pure substances. They are mixtures. They are definitely going to be heterogeneous. So these have something dispersed in another solution, and it makes this weird um, you'll see. All right, so the dispersed phase is going to be either a solid, a liquid, or a gas, and the dispersing medium can either be a solid, liquid, or gas. So you can have all these different combinations. A very special type of colloid is referred to as an emulsion. It's a special classification for liquid-liquid colloids. An example of this is going to be mayonnaise. It's going to have liquid oil and liquid eggs that are held together and not going to separate through adding some lemon juice and acid or some mustard seed, because they are emulsifiers and they will allow for those two things to come together. But you can make some mayo from scratch at home. All right, a very fun little mini experiment we do in class is talk about shaving cream and what type of colloid a shaving cream is. A lot of people think it's a solid or a liquid or a gas or a soliquid and mixture of all three. All right, if you were to take some shaving cream and press the little button and get it to come out and put it on a paper towel, it will keep its shape. So that means it's going to have a property that's going to be a solid. If you look at it under a magnifying glass, it has like a whole lot of bubbles. And that whole lot of bubbles means that, oh, wait, no, maybe it's a gas. And if it's left out to dry out, it will leave like this sticky gel behind. So if it's drying out, maybe the liquid left. So what is shaving cream? Shaving cream is going to be a gas liquid colloid. Shaving cream, whipped cream, you are basically having some type of accelerant push a gas through the liquid. All right, so this is going to be your Ready Whip, and you can actually do this by hand by having your whipped cream in the bottom and then a whisk or an egg beater, and you're basically just going to incorporate a lot of air into the fat of the cream. Liquid colloids are also a thing, as I told you about with mayo, but milk from any mammal is actually going to separate out. You also see this sometimes in yogurt, that healthy whey protein is going to be that yellow liquid up at the top, and then you end up having your curd part down at the bottom, which is the white part. And if it's not pasteurized, they actually do separate. Solid liquid colloids are going to be like blood or ink. When the liquid dries off, it's left with the solid residue, which is going to be your scab or whatever you wrote or colored in on the paper. Liquid gas colloids are things like fog and mist and clouds. Solid gas colloids are going to be soot or smog. That's going to be real bad to breathe in. That's what's going to make all the pollution. That's why there needs to be filter on cars and treatment plants so that we aren't putting all of the stuff into the air. And then lastly, you have gases or liquids that are in your colloids, like styrofoam, pumice, which is that volcanic rock. I always bring in some of the volcanic pumice that I found on the beach in Japan. Oh, it's so cool. It's like floating rocks everywhere. And liquid solid stuff, which is going to be your jelly, jello, gelatin, and all that good stuff as well. All right, if you want to spend some time reading this slide, make sure that you push pause. I'm just going to leave it there for a couple seconds, but it goes through a lot more different types of colloids, like solid ones, which are going to be your alloys and glass and gemstones and all that kind of stuff. All right, so how can you tell the difference between a aqueous solution, a suspension, and a colloid? That is something called the Tyndall effect. The Tyndall effect is going to be when you shine light, a light beam or a laser beam through your substance. Okay, and the suspended particles will catch them up and it basically lights up. So this would be your aqueous substance, this would be your colloid, and you would see that the light goes through here, but it definitely illuminates here, and this is going to be the Tyndall effect. Very common example of this is going to be driving. Okay, driving when there is fog. You don't use your high beams when you are driving in fog because you don't want it to illuminate all of the water particles that are in the air suspended in the gas. You want to use your fog lights, which are at the bottom, that shine on the road so that you don't see a whiteout and you can see Bambi or whoever is crossing over the road and making sure that you are good and safe. Okay, so this little chart right here actually summarizes everything really nicely for you. Again, push pause if you need to read it, but the differences are solutions, our colloids, and our suspensions. Okay, solutions are homogeneous, the same and consistent throughout. Colloids are heterogeneous, and so are the suspensions. These are going to be the smallest of our particles that are going to be dissolved. Colloids are going to be in between, and your suspensions are going to be your largest particles. They don't actually dissolve. Okay, and neither do our colloids. They don't separate while standing are your solutions, but sometimes colloids do, like if you have a gas, but the particles tend to settle out in your suspensions. But the big thing is down here with our Tyndall effect. Okay, your solutions do not scatter light, but colloids and your suspensions do. All right, so that's a big difference. All right, and the last thing that we're going to talk about is a special classification of our aqueous substances, and that's going to be whether they are electrolytes or non-electrolytes. Okay, so a lot of people think that electrolytes give you energy. They do not. What an electrolyte does is that they allow for your body to conduct an electrical current. Where would you need an electrical current? From your brain, from your nervous system down your spine into your muscles. So it is going to allow for your brain to send those signals into your arm muscles or into your leg muscles so you can run, jump, throw, and all that kind of stuff. All right, so what's an electrolyte? An electrolyte is an ionic compound. Yes, the fundamental of chemistry. And a non-electrolyte is going to be a covalent compound. So ionic compounds are going to be the metal nonmetals, left side, right side of the periodic tables. So salt, your copper sulfate, all of your acids and bases. Acids begin with H, bases end with OH. Um, are all going to allow for conducting of this current. Okay, tap water is going to be an electrolyte. That's why it says don't use your hair dryer in the bathtub. So when the lifeguard is going to blow its whistle when they hear thunder in the distance, as annoying as it is because if you're either in the ocean or where you have chlorine in the water, and it's definitely going to conduct current, and you don't want to be in that water when it happens. Non-electrolytes are going to be your covalent compounds, which are your non-metal compounds, and that's going to be sugar, alcohol, and pure water. So that means deionized water is going to be a non-electrolyte. Tap water, electrolyte, okay? And in class, I actually show a lot of examples of this with nothing more than a light bulb, okay? A light bulb that has these two probes and a position for a beaker to put in it. But an electrolyte is going to help your muscles. It's going to circulate the potassium, the calcium, magnesium, manganese, sodium, and chloride. This should be a lowercase l. Ugh, pet peeve of mine when people get those things wrong in graphics. But it will light up if it's going to conduct, and it will not light up if it's a non-conductor. So I show kids tap water, and tap water is an electrolyte, and then I show them deionized water, and the deionized water does not. Okay, Powerade lights up a little bit, Gatorade lights up a little bit more, salt water very little bit because it has a lot of magnesium sulfate and stuff in it if you read the label. Some years the Deer Park water works. It depends on where it was bottled, and some years it doesn't. It's very weird. But something that always lights it up, a good natural electrolyte, is going to be coconut water. So hopefully you like the taste and you use that to replenish it because this stuff has lots of sugar, and sugars are non-electrolytes. All right, everybody. Hope that you learned a little bit about our electrolytes.